All right, so this is hour 2 of Physics 1C for October 27th, and we're going to be talking about a phenomenon that is called electromagnetic induction. And how the motion of a magnet can produce an electric field and cause charges to move through a wire. Okay? So some of the implications of what we're going to be discussing here today is, where does the electrical power that comes from your wall come from? You know, maybe that's a question you've asked before. Like, how is it that when I plug something into the wall, I get power? You know, how is it produced? Where is it coming from? How is power generated? Electricity. We'll just say, how is electricity generated? Because that's really what this is about at its core. We've learned how magnetic fields are produced, and they're produced by moving electrons. And it's going to be kind of the reverse, that electricity itself is generated on a kind of like commercial scale, the kind that you buy by moving magnets near coils of wire. Okay, so that's kind of something that you should be able to answer by the end of today. You'd also hopefully be able to answer by the end of today's class what direction that current is going to flow. All right, so this phenomenon was first... I'm always worried about saying this because I feel like maybe somebody else did it first, but this phenomenon, I believe, was first discovered by Michael Faraday. If it wasn't, he was certainly responsible for investigating the phenomenon at an exhaustive level, okay? And the general phenomenon is this. If I take a coil of wire, so let's say I have some coil of wire here, and it's wrapped around like this, and let's say that this coil of wire forms like a bunch of loops, the more the better, as we will find out, then the phenomenon that Faraday noticed was that when you bring a magnet near a coil of wire such as this, so if you take a magnet, if I take a magnet right here, what's this doing? I don't want to copy the content library, that's okay. So if I take a magnet, let's say this is the north end right here, and then this is the south end over here. What he found is that if you move this magnet really anywhere near the coil, so if we take this magnet and we move it in this direction, for example, that what will happen is it will actually cause the charges within the wire. Now, the idea here is this wire has no current flowing through it. It's just a wire of some type. Maybe it's a piece of copper that's been wound around a tube or something like that. If you move the magnet inside of here, you're going to get current flow inside of here. Now, I'm going to have to think for a second. I believe the current is going to flow this way. I'll write it with a different color. You're going to get... I know that color's not good. Use blue. You're going to get current flow that's going to go around like this and then up like this. Let's see, back this way. So we're kind of going from the other direction, right? So it's going down this way, up this way, down this way, up this way. So there's going to be current that flows when you move the magnet into the field. Did I do that right? Yeah, absolutely. We'll talk about how I know what direction that's going. That's called Lenz's law. But the general idea is that the motion of the magnet, if you move the magnet near the wire, you're going to produce an electrical current. And this phenomenon is what's called induction. It is the phenomenon behind which induction heating works. There are things called induction stoves. Maybe we'll know more about that later on today. Has anyone here used an induction stove before? Anyone ever been to someone's house or where they have that? What do they look like, Mr. Meowers? A lot of you have, apparently, yeah. They heat up really fast? Uh-huh. Metal coils. They work off coils. Yeah, coils like this right here. What do you know? Yeah, okay. So an induction stove is an example of something like this. Another example is... Let me ask you guys about this. Have you ever put your hand on top of an induction stove? Does it get really hot? Okay. All right. So another example of an application of induction is wireless charging. So do any of you have phones that have wireless charging where you just like set it down on a little thing? You don't have to actually have contacts, right? So really, really kind of great. I mean, I will say this is something we're talking about. This was discovered by Michael Faraday. Faraday was an English scientist who came from He was not a very rich person. The fact that he even was able to manage to go to college was something that would be kind of not common for people coming from his status. He didn't have a lot of money, but he was really good at science. He's definitely one of, in my opinion, the more impressive scientists in history because he, well, I'll talk about him more in a second. But it was discovered by Faraday. I want to say something like between the 1830s and 1850s, somewhere in that region. So we're going to say 1840, and that may be wrong. Maybe it was closer to 1850. But just think about how old this is, how old this phenomenon is, and think about how new some of the applications that I just described are. Like, induction stoves weren't really common, I don't think, 30 years ago. And I know that wireless charging is not something that was very common a long time ago. Although I will say that, like electric toothbrushes, those use the same phenomenon too. They use the induction for charging as well. There's no contacts on an electrical toothbrush, which maybe it's obvious why, but you probably don't want something that has electrical contacts get wet, right? So it also works off of this type of induction thing where you don't need contact, but you can still produce this. I don't know how much I've talked to y'all about Faraday or if I'm just thinking about my other classes, but Faraday was really amazing because what he did was he experimented with this combination of magnets and wires in all kinds of different shapes, and he basically tried to figure out, well, how do I make this induction phenomenon the strongest? What do I need to do to make it the strongest? And he kind of figured out that there's a nice little relationship called Faraday's law that governs this. And the things that go into it, the things that affect this, are the following. Basically, he found out that you can induce a current or an EMF. Okay, so E represents EMF in a wire when one of we'll just put a little arrow here to say that you can induce an EMF in a wire if one of three things happens. Okay, if the magnetic field changes, if the area of the loop changes, so what would be something like that? Well, you could say, suppose I have some magnetic field. So let's say I've got a magnetic field in some region of space here. Okay. And let's say in that region of space I have a loop like this. And if you were to pull, so this is a wire. Sorry, if you were to pull like this, that wire would shrink in size, right? And the act of the area of the loop changing would actually induce a magnetic field. I need to be more careful. There's a magnetic field here. That's the B. Just by changing the area of that loop, you'll actually get a magnetic field. Okay? So if a magnetic field itself changes, this could be represented by moving. It could be moving. Okay? It doesn't have to be changing in time or anything like that. It could just be moving. In this case, the magnetic field changes in space. The area of the loop can change. And there's a third possibility. Can anyone guess what the third possibility is? What if the magnetic field stays the same, the area of the loop stays the same? How could I maybe move my loop or move my wire without altering the size of the field or size of the area? Shrink the loop is one of them. That would be the area of the loop changing. The current, rotations, yeah, rotate. The other possibility is the angle between the magnetic fields and the area of the loop could change. And that would be, this is the primary method that we use. This is the easiest thing to do. It's a lot easier to just take a fixed magnetic field. So we'll do some problems with this. So like you take two magnets like this, right? Big North Pole right here. And then you wrap it around. So the South Pole, another magnet's right here. This produces a nice, really simple magnetic field that's kind of straight in nature. This produces a nice magnetic field that's kind of like this. I don't want to draw a lot of lines, but there could be as many as you want to draw inside of there. So now what you do is you just take a loop and you put your loop inside of here, right? And ideally you want to kind of get a whole bunch of turns of that loop. So you get a coil, just get a big coil, right? And now you just rotate the coil. And if you rotate the coil, that's also going to produce a current in the wire. So that's a generator. That basically is what a generator is. And I believe we've actually talked about motors in this class, right? And motors operated off of the same principle, right? A motor was the idea that if I pass current through the loop, it would naturally rotate. But if you actively, like, let's say you put a hand crank on here, right? Put a little hand crank, and you just spin it around in a circle, then you're going to get current generated inside of here. And that is what a generator is. That's how we commercially generate power. That's how electricity is primarily generated in the United States. And we could talk more about that process. I think we have. I don't know if it was my 1B class or if it was this class this semester, but we'll come back to that. Now, I can talk about this stuff and I can draw pictures, but I think it's better if you see how it works. There's two different ways to do it. So I'm going to show you a video first, and then we're going to play with this to get ideas for what's going on. Okay? So here's a little short 4-minute video. I don't think we need the sound for this, but I'm going to put it on anyway. Okay. 31. Okay. There we go. Notice in this case, as he's saying here, oops, that you get the same effect if you put levitating barbecue. You're welcome to go check that out yourself. We're going to look at a video that's kind of like that in a second. Yeah, it's kind of interesting. The same phenomenon you get even if you put a coil around a coil. And this other video is all about, look at this video. I don't know about this video here, but we'll watch this one later. I don't think we're ready to watch that one yet. Okay. Okay, so you kind of saw in general, he actually derived the equation for us too. We're going to use different symbols because we don't use the symbol psi, we use phi. It's just a small difference, but so in general, that's what we call electromagnetic induction. And we can and you can do this too if you want to. You can go to this website here. It's PHET, and you can try this out yourself. In fact, I'll just copy this and put it into the channel. And we can kind of observe some of the features of how this works with this one. So in this case, we have kind of a visualization of what's going on. I'm going to go back to the defaults of this right here. But what we have here is there's a loop. It's connected to a light bulb. And if we move the magnet into the loop here, you'll see that there's some light that's produced, just like he was showing in that in the video. Nothing happens when the magnet sits still. It's only when the magnet is moving that you see this effect. Whether you move it in or out, the light bulb lights up. However, you'll notice that just like in the video, the voltage depends on kind of how fast you do it. In fact, this voltage meter doesn't go high enough to indicate what's really going on here, because just even a tiny motion of this magnet and it instantly starts moving. And it's a simulation, so that's why it's doing that. But the faster you move it, the bigger effect you get. That's why there's a derivative that shows up here. And you'll notice here that if you go inwards, it goes negative. If you go outwards, it goes positive. I don't think he did this in the video. If you flip it around, if you go in, it goes positive, and out, it's negative. So it's opposite, right? That makes sense? I think it's particularly interesting to look at the field lines right here, because what you can see here is when you're moving this thing in and out here, what's really changing inside the loop? Well, you're going from an area where there's not as many field lines as densely packed, right, to an area where the magnetic field lines are really closely packed. So really the thing that's changing here is not the field. That's not the biggest part of this. It's the flux. It's all about the flux, because like look what happens to the flux as you go through here. Remember that flux is proportional to number of lines, right? So how many lines are passing through right now? There's 3, right? And remember that with flux was equal to like magnetic field times the area, but you also have to multiply by the cosine of the angle between them, right? So these lines are kind of pointing up at an angle, but the lines as we get closer and closer in here, they become more flat. At the strongest point of the magnetic field, right at the tip right here, you have a lot more field lines, right? So you go from 4 lines, 1, 2, 3, 4 passing through your loop, to when you get to this point, how many lines are passing through the loop now? There's like 6, right? And then when you get to here, you get 8. So that change from 4 to 6 to 8 is the change in flux that you observe, basically, that causes this to happen. One thing you can also do with this particular demo that I was noticing is we can see what happens if we move the magnet outside of the loop. Okay? So right now you've got a flux line going in this way and coming out this way, right? Magnetic field line, so there's some flux through here. Notice that if I wiggle this back and forth here, the effect is not nearly as big. The magnet's not inside, but can you see it actually is? It's still wiggling, right? And maybe if I do it fast enough, you can see it more effectively. Can you see that that's wiggling back and forth? But the biggest difference here is, even the same thing would happen if I go up and down here. In fact, it looks like the effect is even bigger as I go up and down. But yeah, that like one line that runs through it there, you're just not getting a very big change in flux. You need to have like a lot more of the lines passing through. Even if we just get a little bit closer to the loop, now you've got a lot more lines that are passing through here, and your flux starts to change. There's this other setting on here too where we can see what happens. There's now 2 loops here. I don't know if that particularly helps to understand anything. So that's something you can play with on your own to get a feel for this. Personally, I think that exploring stuff like this on your own is pretty helpful to understanding how physics works. The other one, I believe we saw this before, right? This one we've seen before, right? The rotation of the magnet near the coil. I think we showed this one before, right? Yeah. But now maybe you have a better understanding of why this is occurring. You know, your field is changing, right? And that if you look deep inside of here, it's like there's a bunch of little rotating magnets. They're not really rotating magnets. It's just it's the magnetic field, right? And another thing I'd like to point out here is, in case you doubted if the magnetic field was a real thing or not, well, let the light kind of like shine and show you that it is a real thing. You know, it's not just that magnets attract things. They actually produce these fields in space, and the motion of those fields can generate real circumstances. You know, they can make these things light up. They can generate electricity, right? So that is Faraday's law. And we can do... Does anyone have any questions so far? Here, let's write out Faraday's law in our own the way we would write it in this class, the way you're going to see it show up in your homework in the book. So Faraday's law states that the EMF that's induced, the induced EMF, I'll write it like this, is equal to, there's a negative sign, we'll talk about where that comes from, multiplied by the number of turns in the coil, multiplied by the time rate of change of the magnetic flux. And to connect this with what we had said slightly higher here, that the 3 things that matter in this, remember that magnetic flux is defined as the magnetic field multiplied by the area of a loop that we're talking about, and then multiplied by the cosine of the angle between that magnetic field and the loop. So you could expand this out and say that this induced EMF, we'll just write it as IND, should be negative N times the time derivative of the magnetic field times the area, and then times the cosine of the angle between them. Now this really only applies when the magnetic field is constant. Of course, there's the other definition of flux, which, you know, you might use this sometimes, but most of the time we're just going to use the upper one, where we do, not a closed. We just do a surface integral of b dot dA. Usually, for almost all the homework problems that you do, this is going to suffice. But yeah, that's Faraday's law right there. And it tells us that the induced EMF arises anytime the magnetic field, the area, or the angle between them changes in time. That's Faraday's law. I don't know if Faraday actually wrote this down. I think I've read somewhere that it's also called Henry's law, and you heard him mention in the video that there was a scientist, Henry, that had figured this out as well. So Faraday wasn't very mathematical in terms of the way he would present information. He was more kind of would describe the phenomenon that he was observing, and he left the mathematics up to other people in a way that's kind of partially probably why you know Maxwell's name, maybe more than you know Faraday's name, is because Maxwell was responsible for kind of putting together all of these ideas. And, you know, Faraday kind of laid the groundwork for him, though, because he kind of showed the phenomenon that Maxwell needed to describe with the mathematics, right? So there we go. That's Faraday's law. And I think the best way to kind of introduce this is to just do a problem so we can see how we would apply this here. So let's do that. Anyone have any questions? I wish I knew better what it causes this thing to come up, or I wish that it would just stay. There it goes. All right, there's a lot of problems we can do with Faraday's law, but we're going to do this one. And what we'll do is we're going to do one problem And then we're going to introduce what's called Lenz's law to describe an answer of what direction does it point, i.e. where does this negative sign come from. Okay. And then we'll go from there and we'll solve a lot more problems. Okay. So EMF and current induced in a loop. So we've got a little loop of wire right here. It is connected up to an ammeter. The total resistance in the circuit and the meter is 5 ohms. The area of the loop is given right here, 120 centimeters squared. It says the magnetic field between the poles of an electromagnet, so the north and south poles of the electromagnet are here, is uniform in time, but is what? It's uniform at any time, but its magnitude is increasing at a rate of this. So it's uniform as in straight, but the field itself is increasing over time at a rate of 0.02 teslas per second. The area of the conducting loop is this. The total resistance is 5 ohms. Find the induced EMF and the induced current in the circuit. If the loop is replaced by one made of an insulator, what effect does this have on the induced EMF and the induced current? Okay. Those are the 2 questions. All right, let's write down Faraday's law. Okay, we can kind of see all the variables here. Is this large enough that you can actually see what those things say? Maybe if you're looking at this on a phone, that might be hard to see. So in this case, we have an area for our loop that is 0.012. Meters squared. We have a magnetic field that's changing in time at a rate of 0.020 teslas per second. That's just the rate at which the magnetic field is changing. I think it's increasing. Yeah, it's increasing. And also we know the resistance, so we use the letter R for resistance, of the wire and all of the loop is 5.0 ohms. Okay. Our goal is to find what is the induced EMF in the loop, as well as what is the induced current in the loop. It's already kind of showing us the direction that that current would be. We'll talk about that in a bit. So what are these going to be? So we're going to apply Faraday's law. This loop only has one turn. You can see it right here. It's one turn of wire. So we'll have 1 multiplied by the time rate of change of the flux. I'm just going to write in here ddt of, I'll leave the negative sign on there too, ddt of b times a times the cosine of the angle between the two of them. In this problem, you can see the direction of the magnetic field indicated by the blue lines here. So in this case, these blue lines here represent the magnetic field at a moment in time. You can see that the magnetic field lines point in the same direction as the area vector of the loop. And that means that the angle between the two of them, theta, is going to be equal to 0. In addition, the area of the loop is not changing. It's fixed. It's only the magnetic field's changing. So I'm going to pull the area out of the integral, or not integral, but out of the derivative here. So we'll end up getting the EMF is going to be negative. Let's see, what do we have? The area comes out, and then we're just multiplying this by the time rate of change of the magnetic field, of which we have both of those. What I said was that how many loops of the, so n represent number of loops, how many loops of wire are there here? Yep, there's just one. It's right there. Okay, so negative a times dv dt. And this is going to give us an EMF. So the area, and we'll work out the units too for this first one. So it's going to be 0.012 meters squared. And we're multiplying that by time rate of change of the flux. There it is, or the field, sorry. 0.02 teslas per second. And then we've got that negative sign there. I'm leaving the negative sign on just because, but we're going to get rid of it at the end. We're just going to look at the magnitude. All right, so there's that, and that's going to give us an answer. What is this going to be? So it's going to be 12 times 2, which is 24. And it's going to be 24 times 10 to the negative 5, or 2.4 times 10 to the negative 4, maybe? That look right? Can anyone calculate it for me? Okay. I'm just going to say this is the magnitude of the induced EMF, okay? Now, the units of this should be what? What should the units of this end up being? Tesla meter squared over second. If it's going to be an EMF, it needs to be in volts, exactly. So let's see. Let's test to see if that's true or not. Okay, what is Tesla meter squared per second? Okay, Tesla. I'm going to write this down and then I'm going to check to see if it's true. I think it's a Newton divided by an amp times a meter. Does that sound right to people? Does Newton over amp meter sound right to you? You don't know, maybe? What equation could I use to check if that's right or not? If I didn't know. Obviously, you can look this stuff up on the internet. That's whatever. I'm asking more like, how could you figure out for yourself if you weren't sure if that's what a Tesla was? What equation could we use that we know about Teslas that says something about magnetic field? What's an equation? What's a simple equation we have that has magnetic field in it? Maybe something we use today. Not this one, but another one. It's a simple equation that has the magnetic field inside of it. Anyone remember anything? Any equation that has a B inside of it is fine. What about the force equation? Do we remember a force equation? Yeah, exactly. That's the one I'm thinking of, Pasta. Exactly. So F equal QV cross B, right? So let's drop the cross product because we're just looking at the we just want to know the magnitude of B, right? Or the unit. So B then is equal to force divided by Q times V, but force would be newtons divided by coulombs times meters per second. That's going to be 1 Tesla. Okay, but then yeah, so coulombs per second is like amp meters, so I think that we're good. I think it's the same thing. You should be able to see the one step from here to here is that coulombs divided by seconds is what we call amps. And then if we do that, we can solve this out. So one of the meters squareds cancel here, and it looks like we get newtons times a meter divided by an amp times a second. And then, as Mr. Meowers is saying, a Newton meter would be a joule, and we're dividing it by an amp times a second. I think an amp times a second is a coulomb. And if you remember, this was our definition of what 1 volt was. 1 volt was a joule per coulomb, right? So this does check out, and our unit there does end up being 2.4 times 10 to the negative 4 volts. So by taking the time rate of change of a magnetic field times an area, Tesla meter squared over second, that's another way to write a volt, basically. Okay, so that's our induced EMF. And I've dropped the negative sign now because we haven't talked about what the direction's supposed to be. In the picture, they would have you believe it points in that direction. And I believe that direction is actually correct now that I look at it. So that's good. Now, the second part of the question was also to find the induced current. If I know what the induced EMF is, how can I find the current? It's going to flow through that wire right there. I know the resistance. I know the EMF. What's the connection between resistance, EMF, and current? Or resistance, voltage, and current? Yeah, V equal to IR. So I'm just going to write it as E equal to IR. The E and the V, they mean the same thing. That gives us that we take the EMF and we divide by the resistance, and that's going to give us the current. So in this case, that means we take this value and we divide by the resistance of 5 ohms, and we'll get something out of that. 5 into 24. Why couldn't it just be 2.5? That would be easy to do. What would this be? So we take 2.4... and we divide by 5 ohms. Let's see, I can multiply by 2 over 2. That'll make this simpler. 4.8 over 10. So I think it's going to be like 4.8. If we're dividing by 10, it's going to go down. 10 to the negative... No, negative 5, right? Is that right? 2 over 2. I think that's right. Okay. Really tiny, right? Super tiny. I mean, we could write this in a different way. This would be like, let's see, if we put a 10 to the negative 3 in here, then we'd have to multiply this times 2. So it's something like, ooh, I'm going to get that wrong. I was going to say 480 millivolts? Milliamps? But I think it's microamps. I think you want to say it's like... So if I make this 10 to the negative 6, I have to multiply this times 10, right? So yeah, it's 48. 48 microamperes. That's the best way to write that, I think. It's not very much, right? But remember that this is just a physics problem, and really, we could easily increase the amount of current that was generated in the spire if we want to, by simply going back and instead of having a 1 right here, we could have just put 100 turns, like you saw in the video. You saw how impactful that was in the video, that if you increase the number of turns, you just massively increase the output in a way. Just think about how simple that is. Oh, I'm sorry. It's current. I'm sorry. Yeah, it's current. My bad. I always know I've made a mistake when there's a lot of people typing at the same time. Thank you for catching my mistake. I appreciate it. Sorry about that. So it's current. But again, it's tiny amount of current, right? That's a tiny amount of EMF. But again, we could have made this current much larger if that was our goal, if you were designing a generator, simply by just increasing the number of turns right here. The number of turns, just amplify it, right? Put 1,000 turns in your wire right here. Just a bunch of a coil, right? You're just little tiny coils, and you'll have 1,000 times as much current if you need it. All right. Anyone have any questions? Now, I want you. Okay, we're gonna have to do this right now because I can't not ask this question. What do you notice about if you point your thumb of your right hand in the direction of this magnetic field here, up, right? And you wrap the fingers of your right hand in the direction that your right hand would normally go. What direction would your fingers of your right hand wrap relative to this current? Same direction or opposite direction? Opposite. Can you all see that? Make sure you can see that. That is what the negative sign means. That is what the negative sign means. Does that make sense? It's opposite to what? It's opposite to this thing. Right? What if dB/dt had been... So what did it say? The magnitude of the field is increasing, right? So this is increasing. The negative sign stays there. If this dB/dt, if I threw another negative sign in here, like if it was negative, if it was decreasing at a certain rate, negative, you get a positive. And what I'm going to tell you right now is that if this thing had said it was decreasing, the current would have been flowing the other way. That's what the negative sign means. That's what we call Lenz's law. That's the next topic, basically. Is that if the flux, okay, is increasing, the negative sign is going to stay there. If the flux is decreasing, well, you get negative times a negative. You get a positive. We'll go into more detail about that, but that's what the negative sign means. Okay. Like, again, I'll go into more detail about that in the next hour. You read it in the book, but the picture they showed didn't make sense. Yeah. Okay. Did what I just said kind of make sense a little bit? If you think about it just in terms of positive and negative numbers, we'll go into a lot more detail in a second. But that's basically the idea. And this is a very good problem to kind of identify. We call that Lenz's law. Okay, one last part of this problem. It says, if the loop is replaced by one made of an insulator, okay, so it's an insulator now, what effect does this have on the induced EMF and the induced current? Okay, and I think this is actually maybe part of what this picture is supposed to be here. What if instead of a piece of copper in here, what if we put a piece of plastic and attached it up to our ammeter? Do you think that we'd get any current readout on our ammeter here if I put a piece of plastic between these 2 points instead of a piece of metal? We know plastic doesn't conduct electricity very well, right? It also doesn't conduct electricity. There you go. That's the exactly right answer, Mr. Miyares. Mr. Miyares has said that wouldn't the resistance be very high? Okay, so if it's an insulator, yep, R would be big. Resistance would be big. So now you're saying voltage and current would be low. Let's check that out. It's definitely the case here that if we're doing E over R, this is going to lead to I equals low, right? Really low. Not microamps, but maybe, picoamps or something. I don't know. But yes, as Ash says, the voltage would actually be the same. The EMF is the same. So it's really counterintuitive, right, Mr. Miyares? The voltage is there. It's just that it's not enough to push the charges of the insulator around because they don't move as freely. You need a big EMF, right? It's like you need a really big EMF if you want to shock yourself. So yeah, and I find this really fascinating. Just think about this. That means, air is an insulator, right? Yeah, the difference in potential is the same. The current just isn't flowing as fast. That's right. Think about this then. This is really, what I'm about to say is kind of, you have to really use your imagination here, okay? So, in the region of space around this magnet, okay, there are EMFs, right? There's an electromotive force. There's a potential in the air, just in the air around it. There's literally a potential difference in the air. So you can imagine that there's these little currents probably not moving very fast or even at all. Probably the random fluctuations of the air molecules due to temperature enough to make them zip around. But yeah, like right there in the middle of the air, you got this EMF. So that's going to be something we're going to get to on Thursday night. We'll talk about how there's an electric field just generally produced there. Well, I think we're going to watch this other video because I would like to know what your opinions on this video are. I found this one, and here I kind of like to know what you think is happening here. All right, let me change the windows so you can hear it because I think there are some audio sounds on this one. Did I do it? Am I on the right one? I'll just check by switching videos. Yes, I think I'm on the right one still. Okay. So, they say this is an electromagnetic induction demonstration. I want to know what y'all think. It's a wire. That is just a piece of iron, as far as I understand. I do not believe that's a magnet. That doesn't look like a magnet to anyone, does it? It looks like a piece of iron, right? All right, so it's just a wire, so it can't light up the bulb, right? He attaches something that he doesn't explain what he's attaching, which is my favorite part of this video. But you see a spark, right? So there's clearly an electrical connection, right? But this is kind of cool, actually. Watch this. He attaches a McMuffin to make the magic work. I do not know what a McMuffin is. Isn't that cool how it like snaps in there like that though? I think that's really neat. Now he's gonna make some changes on wiring that we can't really see what's happening. White bulb got really bright there. This is a coil around a coil. Is it? Oh, okay, I'm gonna let him finish. So this was I think that was no, I think maybe this is a third connection possibility here. The light's on the whole time, right? Let's go back a little bit. No. No, how did I lose it? Here. No, I don't want to watch your video. Ugh, it's even the Google voice. It's even worse. This is not what we just learned, no. But he calls it an electromagnetic induction demonstration, so like, take that for what you will. I want to go. No, I want to go back to your video. Oh God, this video with 1,500 views needs a. Okay. So when you first connected it, did the light come on? Like here, does the light come on? It does, right? Yeah, it does. Okay, the light does come on there, and then when he pops this thing in here, the light gets brighter, right? Now it's clear what he's doing is he's attaching. Look, as best I can tell, I don't think it's attached to a. Okay. It's attached to an EMF source, right? Saying that it's a battery, we don't know if it's a battery. Based on what I'm seeing here, my guess is he's connected it to an alternating current generator, i.e., like to the wall socket, basically. I think that's what he's attached it to. But it's clearly a power source, right, Ash? It's very clearly a power source because the moment he connects it, like here, the light bulb's off, and then it's going to turn on here in a second, right, when he connects it. You see it come on right there, right? It will light up, but really what I think he's generating, what he's trying to show here, is that the insertion of the core here, what it's doing is it's enhancing the electromagnetic induction. So, what are you saying? The alternating current generates a magnetic field in the bar. Yes. Yes, I think that's right. I think that's part of why the bar is attracted to it, right? Is the bar becomes kind of magnetized. Yes, the fluctuations of the alternating current cause changes in the magnetic fields, exactly. So I cannot tell based on... Yeah, do you get it now? That's why AC is necessary, right? That's why AC is so valuable. We're going to talk more about this in the upcoming lectures and stuff like this, but like, AC is like... It automatically makes Faraday's law work, right? We have a whole chapter on alternating current, and one drawback to your guys' textbook. Oh, I missed Ash's question. What if they didn't add the second wire and just use the magnet? What would happen? Would nothing happen? He doesn't have a magnet, Ash. That's the key here. He doesn't have a magnet. That is just a piece of iron. So you could produce, right? So, yeah, but yeah, AC is necessary because it effectively makes it so that Faraday's law can work. You know, we'll talk more about that. But yeah, having an alternating current. See what I think what's happening here that like he was trying to display. Where was it? This part right here. I believe there's a secondary coil right here. So it's like a coil wrapped around a coil. And one of the coils is hooked up to the electromagnet. And one of the coils is hooked up to the light bulb. Well, they're both hooked to the light bulb, actually. I think they're connected in series, actually. And there's like... See, it says spool of wood wrapped 2 coils of copper wire separate between them. When in the central hole a spool is inserted an iron coil, the coil reacts by creating an electromagnetic field. Conversely, by exchanging the terminals, the electromagnetic force is canceled at the terminals of the wire. So that's his explanation. And then some other YouTube link. I don't know what this is. Anyway, it's kind of a cool video. Just things you can do. You're dropping a dislike. You think I should dislike this? I'm gonna give it a like. It was at least, I don't know, somewhat informative. We should probably take a break. It's 8:05, so we'll go until like 8:15. Does anyone have any questions? Any questions at all?